Okay, so today is lecture 9 for data mining at Google. There is a midterm exam for the Stanford students this Thursday, so we're not going to have class Friday, and I'll send around an email reminding you about that, just so we stay in sync with them. I started to talk about Simpson's paradox last time, so we're going to review that today. I gave you a sort of a toy textbook example last time. I'm going to give you the same numbers in a real example this time and get you to think about the implications of that. I have the homework solutions. I'll just show you the link to that. I don't think we'll go over any of those specifically unless there's a few that you want to see. So we'll probably get done pretty early today if you're curious to see what's on the midterm. I can also send around the midterm exam after the students take it to the email list if you want to take a look at the types of questions and see how much you've learned. But basically I want to go over Simpson's paradox today, which shouldn't take too long. So that's about the midterm. Okay, so chapter 6 on association analysis. The Simpson's paradox is talked about in section 6.7, I believe. And this was the example I gave you last time, where there's a third possibly hidden variable, right? So the variable could be something that's in your data but you haven't thought about. It could be something that you could measure but have chosen not to, or it could be something that you're completely unaware of that's causing the paradox to occur. And so it occurs when this third possibly hidden variable causes the observed relationship between a pair of variables to disappear or reverse directions. So for an example here, I'm looking at the relationship between who is taking the shots and how many are made or missed. So those are the two variables that I'm looking at, make or miss versus me and my friend. And from the aggregate data, I see that I'm making 50% of the shots and my friend is making 40% of the shots, which leads me to believe that I am the better shooter, okay, because I've made a higher fraction of my shots than he has. And for some applications, that would be of interest, right? If I had to say, okay, I need to pick one person to go into the game to shoot a shot. Well, if they have to create their own shot and they have to play in a similar style to what they played when my friend and I played, then maybe I should go into the game because I'm going to have a higher percentage of made shots. However, if I'm putting a person to go into the game to take a specific shot, if that's the question, if who is the better shooter means who is the better shooter for shooting a specific shot, then really I should control the data for the type of shot. And the type of shot in this data was whether the shot was far or close. And what you see is that sort of in aggregate, remember, in aggregate I'm a 50% shooter and my friend was a 40% shooter. So in aggregate, when we're left to our own devices to pick our own shot and shoot our own shot, I make a higher percentage. But when you control for the distance, that's when things get different, right? So me from far, remember I was 1 out of 4 from far, so I was 25% from far. And my friend from far, let me go down here to my friend, split these between me and my friend. My friend from far, he shot 5 out of 15, so he is a 33% shooter from far. Right, 33.3. So he's a better shooter than me from far away. And then you look at close, and I from close am 9 out of 16. So 9 out of 16 from close, that was 50, what was that, 54%, 9 divided by 16, 56%. 56% from close. And my friend from close, he is 3 out of 5, so he's 60% from close. Okay, so what's happening? My friend is a better shooter than me from close up, and he's a better shooter than me from far away, right? 60 versus 56, 33 versus 25. So he shoots better than me from close up, and he shoots better than me from far away, but I wind up having a higher overall percentage. Why? Because I'm shooting more shots from close up, and he's shooting more shots from far away, and the far away shots are harder to make. So obviously, if you fix these two ratios to be the same, this thing couldn't happen. But as long as I'm allowed to shoot more close shots, which are harder to make, which are easier to make, sorry, and he's shooting more far shots, which are harder to make, then I can wind up doing better in aggregate when in fact he does better from each specific distance. And again, it's not so much a paradox as it comes back to really what is your question. You know, when you say who is the better shooter, it sounds like a simple enough question, but really what you have to do is ask the person who's asking you this question, why do you want to know? Right? It sounds like you're being defensive. Who's the better shooter? Why do you want to know? But it's important because you say, if you want to know because you're going to pick one player to go into the game and create their own shot, then I'm the better shooter. But if you want to have one player go in the game to shoot a specific shot from a specific distance, which may still be undetermined, then my friend would be the better shooter. So it really depends on the question. Now again, this is just the toy textbook example, but I wanted to use the same numbers and show you sort of a more realistic example. So let me see if I can tell you this story without sort of saying anything that I can't say. So a search engine labels web pages as good or bad. Okay, so this, you look at the web page, you say that's a good page, it's a bad page, some measurement of quality. Okay. A researcher is interested in studying the relationship between the duration of the time a user spends on the page. So if you were able to measure how long someone spent on the page, maybe you can think about putting people in a lab and looking how much time they spend on the page. And so you can record that as long or short, and then you know the good or bad attribute. So we have two variables, right? How long they spent on the page, long or short, and then was the page good or was the page bad? And so me and my friend are taking the place here of good and bad. Okay, so let me, here, actually, you know what? I'm going to leave this example up and then just sort of redraw everything down here. So let's see. The good pages, right, if I start with good, the good pages are 50% long, right? On a good page, people stay long 50% of the time. And on the bad pages, those are only 40% long, right? So in aggregate, it looks like what you want people to do is to stay for a long time. And this is sort of an open question, right? Because you can argue it both ways. You can say, well, if the page is good, they'll be happy with it and they'll stay a long time. But you can argue the other way. You can say if the page is good, then they'll find what they want right away and they don't need to stay a long time, right? So reasonable people can differ on their intuition in terms of which way this should go. But looking at this aggregate data, it suggests that the good pages are long 50% of the time, whereas the bad pages are long only 40% of the time. So it argues for this case that if it's a good page, they're going to stay a long time. It argues for a positive association between duration and quality. Okay, so you say sort of, you know, period, end of the story, problem solved. And so you say, okay, great. Now how are you going to use this information? Okay, what information, how is knowing that this is this positive relationship between quality and duration going to influence you? Well, they'll say, well, now that you've done all this great work and you've showed us that there's a positive association between quality and duration, because before we didn't know, you know, we thought it could go either way. We thought if they're staying a long time, it could be because they can't find what they want or because they're happy. Now we think it's because they're happy. So now what we're going to do is we're going to track our quality, knowing that our quality has a positive relationship with duration. So we're just going to plot here duration on the y-axis. And on the x-axis, we're going to put, this could be time, right? So day 1, day 2, day 3. And we're going to track the duration over time. And so how am I measuring duration? You know, sort of maybe the total number of seconds people stay on all pages. Okay, some aggregate measure of duration. And then when I see something happen, right? So right here, some time point, something happens. What happens? What am I looking for? Well, someone has changed the search results that are being served, right? Someone has sort of changed the magic formula, and now we're going to serve different search results. So what I want to know is what's going to happen to the average duration. Well, suppose that it goes up, okay? So right here, there's been a change, okay? They changed from using sort of one algorithm to serve the search results to another algorithm. And they say, great, now we know that this change was positive because it resulted in people staying on the pages for a longer time. Okay. The problem is, right, the original question which just said, what's the relationship in aggregate, right, between duration and goodness? You know, they never really told me that this was going to be the specific application. And one thing now, when I see the specific application and I realize what they're changing, okay, has to do with the quality of the results, I know that in particular there's one thing they're not changing that I should probably control for. And one of the biggest influences on whether a web page is good or bad depends on what? The query, right? So if I type in the query Amazon.com, there's a lot of good web pages for that. If I type in the query, you know, what is the biggest country in Texas? Well, Texas doesn't have countries in it, right? So there's probably not a lot of good web pages for that. If I type in AA, BBB, CCC, DDF, right? There's probably not a lot of good web pages for that. So the query arguably is very important. Furthermore, when you see this, right? You see this change. I'm affecting the quality of the web results. I'm not affecting the queries that are being issued. Okay, so the query stream isn't, the changes in the query stream are not something I'm interested in picking up. I'm interested in picking up for the same query, what is the quality of the web results for the same query. So arguably in this analysis, I should not be looking at aggregate data. I should be controlling for query. Why? Because one, I know it's a huge source of variation, and two, I'm not looking to measure changes as a result of the query stream changes. I'm looking at measuring changes as a result of changing results for the same query. So arguably, I know already I should be controlling for query. So then when you look at the data, right, of course, again, it's the same numbers, but we'll tell the story here, right? So break down the good pages and the bad pages into the type of query. Now, there's millions of types of queries. The one thing about whether this variable is even measurable, right? I mean, queries don't come with their own labels. You would have to do some sort of labeling. In fact, you could treat each query as its own category if you want. Here I sort of did an obvious split between adult queries and non-adult queries, but this could be any sort of distinction you want. But the problem is, thinking back to Simpson's paradox, talking about a possibly hidden variable. Well, it's not really hidden, but you would have to do some work to do this classification into different types of queries. So here I just made a classification into adult and non-adult. And what we're going to do is we're going to look at each one separately, right? So the good queries, which are 50% long, if you break these down into adult and non-adult, so adult and non-adult. Okay, so the adult queries are 1 out of 4, 25% long. Right? These are 25% long. Okay, and sorry, so I'm thinking about what percent are long, but they're 25% for the adult queries here. Okay, yeah, they're 25% long. That's what I wanted to say. And then the non-adult queries, if I look at the non-adult queries for the good, these are 9 out of 16, which is the 56% long. Okay, and then let me do the same thing for the bad web pages. So the adult ones here are 5 out of 15% long, 5 out of 15, so that's 33% long for the adult. And then the non-adult, of course, these guys are going to be 3 out of 5 or 60% long. Okay. So what's the story? The story is that if you look at the adult queries, the good ones are 25% long, and the bad ones are 33% long. So on the adult queries, it seems like you don't want them to stay a long time. It seems like the quality and the duration have a negative relationship, right? On the adult queries, the good ones are 25% long, the bad ones are 33% long, so I'd rather have people not staying a long time. To me, that would indicate that I'm giving them good pages. Same things for the non-adult here, right? The good pages are 56% long, and the bad pages are 60% long. So also on the non-adult, I don't want people to stay a long time. If they're not staying a long time, that's positive association with good, right? So there's a negative relationship, again, between duration and quality, which is arguing that if the page is good, they're not going to stay a long time. Okay. So it's the same story as with the basketball, right? Remember the story with the basketball was that my friend shoots a lot more further shots which are harder to make. With this one, the bad queries are much more often adult, which are much more often short. So this relationship I'm seeing between bad and short isn't really that direct. It's really like bad implies adult, which implies short. Okay? So then once you control for the query type and you look at adult and non-adult by themselves, you realize that the relationship completely reverses. So then when you go back to this graph, and you see an uptick in the graph in duration, you say, well, either for adult or non-adult, in either case, this is a bad thing. You don't want a long duration. So it completely changes your analysis, right? Whether or not you control for query or don't control for query. So the question of whether you should be controlling for query really depends on the way in which the data is going to be used. If you're looking at this to sort of measure whether people are, sort of happier as a result of changes in the query stream, then you shouldn't control for query. But if you're trying to see if people are happier for the same queries, which is what we're trying to do, then you should control for the query. Now, controlling for the query isn't that simple, right? As I mentioned to you, first of all, adult and non-adult, queries don't come pre-labeled. You would have to do some labeling. Maybe this isn't enough categories, okay? Maybe you want a separate category for every query. Well, if you're using software packages, some of them only handle so many categories. If you want a separate category for every query, you might things may not work. Furthermore, even though you had a lot of data, for some queries you may not have a lot of data. So what starts out as a lot of data, if you're not really allowed to aggregate, then it becomes, not much data. And then what do you do, if in this case, long is always bad. But what if in some of the queries long is bad and some of the other queries long is good? Then this sort of analysis really depends on which type of queries you're affecting. Some queries you want them to become longer, some queries you don't want them to become longer. So maybe it's not really even a good metric in the first place, because it would depend on whether this change is affecting one type of query or another type of query. So you really, the whole thing of Simpson's paradox, again, I think it trivializes it to call it a paradox and to make these sort of cute textbook examples. It really comes down to formulating the question very specifically. And you look at this question, to me this is an example of a poorly formulated question. Whenever someone says, I want to study the relationship between something, right? Like, you can say the relationship in a lot of different ways, but the question is, once you have the knowledge of that relationship, how are you going to use that information? If I'm going to be using it to track quality by using duration as a surrogate for quality, well, the first thing I know is I should be controlling for things like query, and all these other things come up. So you really need to, when someone says, hey, analyze this data because I'm trying to find out this relationship, or analyze this data, because I want to know this. But why do you want to know that? Is it because you want to know it because who should you put in the game to create their own shot? Who should you put in the game to shoot a specific shot? Should duration be thought of as a surrogate for quality when I make changes that don't affect the query stream but do affect the result? So it really comes down to knowing what you should control for, knowing what you should put in your model, knowing what you should be able to aggregate over, knowing what you shouldn't be able to aggregate over. The other thing, of course, that people have mentioned, I think mentioned last time, is the only way this can happen is if these proportions are different, right? And so in an experiment, from experimental data, this generally wouldn't be a problem because you could control or randomize for such things in an experiment, and you wouldn't let these marginal totals differ by so much. However, data mining is rarely based on experimental data, so this is often always a problem. If you want to know how these ratios have to differ, this is one example I'll show you. The homework, let me just mention this to you. I don't even know if I have an internet connection, so, well, that's the first thing I'll try. I probably don't. Nope, okay, so let me just show you the homework then on this one. So let's see, homework is here, and one of the homework problems I asked, so this was all linked from stats202.com. So you can see here, let's see. Here's a question about this. My friend and I, number 9 here, my friend and I play basketball. I make 70% of my non-long shots and 40% of my long shots. He makes 60% of his non-long shots and 20% of his long shots. Letting PF denote the percent of my friend's shots which are long and PM denote the percent of my shots which are long. What relationship must hold in order between PM and PF in order for my friend to make a higher overall percentage? So if my friend is going to make a higher overall percentage, you know that he needs to shoot fewer long shots than I do, right? Because the long shots are harder to make, and he's worse at them than I am, and he's worse at everything, right? He's 60 versus 70, and he's 20 versus 40. He's worse than I am, but the only way he's going to beat me is if he shoots fewer long shots, right? So his PF, his ratio of long shots, his percentage of long shots must be less than my percentage of long shots PM. So PF has to be less than PM. If you want to figure out exactly what the relationship is, how much less it needs to be, you can go through the math, and it becomes a linear relationship. And again, if they're equal, there's no way it could happen. So he has to shoot a higher fraction of long shots, sorry, a lower fraction of long shots than I do. And in particular, here's the math, right? So you start out, basically, this is how many shots I make, right? I make 40% of my long shots and 70% of my non-long shots. 1 minus PM would be my long shots. He makes 20% of his long shots and 60% of his non-long shots. So 1 minus PF would be the percent of his long shots. So you simply go through, the algebra, and you see that the proportion of my friend's shots, which are long, has to be less than mine times 0.75 minus 0.25. That's what the math gives you. And you could work this out in general by replacing these numbers with just arbitrary constants. And so you see right away, he has to shoot a lower fraction of long shots if he's going to beat me. And it has to be lower by this relationship. So in particular, right, if this were 0, this would say it has to be negative, so it can't happen, right? If I don't shoot any long shots, he's never going to beat me. In fact, even if this was like 0.25, then this would be still negative. So I myself have to shoot a sufficiently high fraction of long shots for him to even have a chance to sort of sneak in there under me and beat me. So that's sort of one of the homework problems. And if you look on the stats202.com webpage, you can click on you can see all the homework problems up there, and I also have all the solutions linked. So you're welcome to go through some of those if you want to practice sort of other problems like this and see the type of homework problems that the students on the class do. And that's sort of the one I asked them to sort of investigate this relationship and appreciate what's going on here. So I think this is all I wanted to say about this one example. I have one more short example of Simpson's paradox to show you, but let me pause and ask if anyone wants to say anything about this example, which before you ask, it's not real. Okay, so that's sort of the story there. So the last one I wanted to say is in the two examples I've given you for Simpson's paradox, all three variables, right, the two variables that you know about right away, right, good versus bad, long versus short, as well as the third variable, type of query, they've all been categorical, right? So we've looked at the relationship between two categorical variables being influenced by a third categorical variable. Now, of course, any of these could also be numerical. Now, all of chapter 6 tends to deal with categorical variables. But you can imagine what the story is when these variables are numerical. And when things are numerical, we're measuring association with correlation, right? The coefficient of correlation. So I already sort of warned you about some things with that. But this would be sort of the classic textbook example involving numeric variables and Simpson's paradox, right? So you look at this and you hear people say things like this, right, all the time, right? Height and reading ability are strongly correlated in grade schools, right? So if my child's tall, he's going to read better, something like that, right? And it gets even sort of more absurd. Like, neither of these are two things, I can really control. But if this was something like, income or something, maybe I should go out and earn more money so my kid will read better or something like that, right? It gets even more funny when there are things that you can control. But height and reading ability, I can't control, but they have a positive correlation in grade school. Why? Well, so, there's probably some third variable. But you look at this and you say, well, in grade school, first of all, the biggest source of variation is not the height or the reading ability. The biggest source of variation influencing the reading ability is not the height, but rather the age, right? Of course, the younger students don't know how to read as well as the older students. So assuming this is a test that doesn't control for age, then you say, well, like, here's all the first graders, right? And they're all very short, right? And they're all they can't read very well, right? So this is how well they read. And so now both of these I'm measuring, both of these are numeric variables, right? Before I had categorical variables, but now they're numeric. So here's all the first graders, and then here's all the sixth graders. And so you say, okay, there's a positive association, right? And so you say, really what you should be doing is controlling for age. This is young and this is old, but you haven't controlled for it, so it looks like there's a positive relationship. In fact, what can even happen, just to go further, right, height and reading ability, you could actually have variables. Well, let's not call them height and reading ability anymore, because these are unrelated, truly, probably, right? But you could have two variables that actually do have a relationship, and it could be a negative relationship, right? So this is a negative relationship. And then in the other group, it could also have a negative relationship, right? So here's the first graders. Whatever these two variables are also has a negative relationship for the first graders. But if you just analyze this data in aggregate and you say, give me the least squares line that fits all the data the best, compute the correlation coefficient for all this data, that's going to be the line, right? It's going to look like it has a positive relationship. So it's the same thing as Simpson's paradox. There's a negative relationship, or in this case, no relationship, if you control for the age. But if you don't control for the age, there's a positive relationship. Now you say, okay, this is a trivial example. I would never make such a stupid mistake. But the other thing that happens is, like, you don't just have 1, 2, 3 variables. You have 1,000 variables. And depending on which ones you put in there, the relationships can reverse or not reverse, could become positive, become negative. So you really have to think, what variables should you be controlling for, and what variables is it okay to aggregate over? Okay, I mean, the solution isn't to control for everything, but in this case, obviously, you should be controlling for age if you're really trying to build a model that can predict, reading ability within a class. Now, if the other question, though, if the question is like, you're going to give me a person, I'm going to close my eyes, and the only thing I get to know is how tall they are, and I have to sort of play a prediction game, predict their reading ability based on only knowing how tall they are, then I would like to use this model. If that's really what the game is, predict how well someone reads, predict how well a grade school kid reads based on how tall he is, okay, if you have two kids, right, and one is, an 8th grader and the other is a 1st grader, and you have to differentiate which one of your kids is reading the story to you, if you knew how tall they were, then it'd be good, right? But if the real story is sort of study the relationship between height and reading ability, arguably you want to control for age. So it really depends on how descriptive is the model supposed to be versus how predictive is it is also an issue too. And if the only thing you get to know is the height, the positive relationship is meaningful. But if you have the age around, you probably want to control for it and learn what the relationship is conditional on the age. So this is my example of Simpson's paradox with numeric variables. Any comments on that? Again, the textbook problems seem trivial, and you think I would never make such a stupid mistake. But when you get a real data set with hundreds of predictors, and you're looking at the relationship between two variables, knowing which other variables you want to control for is important, and knowing that really depends on sort of the problem formulation and exactly what you hope to use the relationship for. So I didn't give you sort of a real example to go with this one, but I gave you that. So let's see. Like I said, in class, in the campus today, I went over the homework problems, and the solutions are posted up online. You can follow a link that takes you to a page that looks like, see if I can show you this, a page that looks like this. And so I have a PDF document with each one of the homework solutions. And so if you go to stats202.com, you can go through those homework problems and read those solutions. I'm not going to take time to go through any of these unless there's any that you happen to see online that you want to see. So we'll probably get done pretty quickly today. The only other thing I wanted to mention is that I have a few sample midterm questions if you're just curious sort of what questions are on the midterm. And I can, if you remind me, I can email you around the midterm and also the solutions if you want to go through and test yourself on what you've learned. This, chapter 1, just by way of review, we basically talked about what data mining is. And this A here is the question, the answer that was in your textbook for the definition of data mining. The process of automatically discovering useful information in large data repositories. These are also viable definitions, but we just sort of got them online. We talked about this nominal versus ordinal interval ratio. So your height measured as short, medium, or tall. This would be an example of ordinal, right? It's not nominal because if I permute the labels, I've lost information. However, it's not interval because I have no reason to think that the spacing between short, medium, and tall is equally spacing. In fact, if you've ever sort of thought about this problem, there's sort of an interesting optimization problem. If you look at so suppose this is the distribution of the lengths of people's feet, right? So most people, their feet are this long, but some people have really long feet and some people have really short feet, okay? So assume these are all like adult males or something. Okay, so now you say, okay, shoe sizes have to be, one, no, there's no one, right? 2, 3, 4, 5, 6, 7, 8, up through, some 16 or something like that, right? These are the shoe sizes I can stock in my store. I'm not going to stock an infinite number of shoe sizes. I'm going to stock a finite number of shoe sizes. So now I have to split these up. Well, you can see it would be suboptimal to split this up equally spaced, right? Really what you want to do is near the mode, you want to have a finer partitioning than you have near the tails, right? Because what are you trying to do? If you're trying to minimize some loss function that looks like, let's just say like the expected value of, your true length of your foot minus the shoe size, the length of the shoe size I give you, like you could look at like squared error loss. You're going to do much better if you have a finer partitioning here and a coarser partitioning in the tails because you can make most people really happy and a minority of the people really upset is going to be better than sort of making everyone equally happy. Okay, so this becomes sort of like an optimization problem. It's actually equivalent to if you were doing quantization, right? So, you can imagine then if I call, if you say very short, short, medium, tall, very tall, super tall, you can imagine that there's no reason to think that the distances between these would be the same. And so you get yourself in trouble when people say, well, I'm just going to code this as 1, 2, 3, and then compute a mean. Because the mean is sort of assuming that this is linear, right? And in fact, it's not. And so that's why we call this thing ordinal and not interval. If the distances were all the same or corresponded to something where the distances were all the same, then we could call it interval, but it's not, so it falls right here into ordinal. Although you'll see people abuse this and oftentimes just sort of numerically code it and compute means and assume that it's interval, but truly it's not. Okay, so that's that problem. Here is a question I put on just to, knock all the people that are sort of zero-based, I guess, right? So I want the third column in R. And so in R is 1 base, so the third column would be data, nothing, comma, 3, that would give me the third column. And of course, square brackets are the right thing to use, not round brackets. So there's just sort of a question about how to do things in R that I put up there. This one, I think we did this one in class. Compute the confidence for the association rule BD implies A. So the numerator would be everything that has the triple, right? How many have A, B, and D? 1, 2, just count up all the ones that have A, B, and D. And the denominator would be the B and D. Count up all the ones that have B and D. And that would give you a fraction which is called the confidence. And then what does this value mean? Well, that means that whatever that number is, of all the people that bought B and D, that percent of the people also bought A. So I put questions like this on the midterm just to test support and confidence. Here's sort of a question about, if you have data that's space delimited, what should be done to allow for a text string that includes a space so that RXL will not split on that space? Well, of course, you should escape it. And if you remember, we talked a little bit about that, and I showed the Wikipedia article for that. And then this question here is the trivial example where I ask people, if I give you some numbers, compute the standard deviation. So I give people 3 numbers, which is sort of the simplest example you can have, and ask them to compute the standard deviation by hand. So there's a few questions that aren't multiple choice on that exam, but you see they're all pretty straightforward. So that's really all I was going to say today, just in terms of talking about how the class goes from here on out. So I told you we're not going to have Friday. What we will do, though, starting next week, is the following. So we've gone through the introduction, the data, exploring data, and then we did a little bit of association analysis just to sort of give you an introduction to that. So arguably, chapters 1, 2, and 3, you could have learned all this in a basic stat class. Association analysis would be not in a basic stat class, but we didn't do anything there that was that involved. I basically wanted to show you one formulation of the problem and the type of data that people get and give you an introduction to that. Most of the textbook really talks about algorithms for solving the problem, so it's not really that interesting either. But we had a brief introduction to that. Okay, so then we have the midterm, which is why we don't have class on Friday. Then chapters 4, 5, and 8 deal with classification. So classification is pretty much my favorite topic, arguably after sort of the graphing. So we'll spend a lot of time on classification. Chapter 4 will basically do decision trees, and then we'll talk about ROC curve, training error, test error, overfitting, basic concepts for classification, and we'll use decision trees as our example and talk about how our decision tree is grown and sort of the greedy approach to growing decision trees and compute the Gini index and then prune based on classification error and things like that. Then chapter 5 talks about alternative techniques. That's where we'll really get into some of the real classification techniques we use. We'll probably talk about nearest neighbors as a simple example. We'll talk hopefully about some of the methods like bagging and boosting. Probably a few comments about support vector machines. I'm not sure how many of these topics we'll have time to get into, but if we've laid a good foundation in chapter 4, then hopefully we can get through these at least enough to show you, oh, here's the R function that calls it, and here's how its performance, and here are the pluses and minuses of it, and here's basically what it's trying to do. And then that'll leave chapter 8 with some cluster analysis, which we'll do sort of the last lecture or lecture and a half maybe to talk about cluster analysis, which I'm not as big into clustering as I am in classification, so we'll spend more time on classification. But these are basically the 2 topics that are left. So no class on Friday, but then on Tuesday we'll start on classification in chapter 4, if you want to look at that. Okay, that's it. Any questions before we take off? Okay, so I'll see you on Tuesday and we'll start classification then.